Effects that we've been seeing in nematic liquid crystals and defects, and also some work somewhat related to what John Ball had mentioned, that or let's say inspired by the fact that for the Oseen-Frank energy we can't obtain through minimization of energies the disclination lines, but for the Landau-Digen's we should be able to, and that's one of the problems that I'm going to talk about here. So studies of thin films in nematic liquid crystals have indicated topological defects of plus and minus 1/2 degree disclination lines in thin films. And also there's been experimental work that shows that as you increase the thickness, that you often get some of these surface bogems that Oleg Lavrentovich was talking about in his talk on Monday, and also that David Nelson has seen in studying very thin films and then going to thicker films. So I'm interested in these types of things. And just to mention a few of the papers that I found interesting. First, in the early 2000s, paper by Lavrentovich and others on Schlieren textures. And here they showed some of these. Let's see if this works. Yeah, they showed here a +1 defect and here a 1/2 degree defect. And also Vitelli and Nelson looked at nematic textures in spherical shells and other type of thin nematic, and found 1/2 degree defects there, at least showed formally that they were stable. So these are interesting papers that explain why these things should be stable. And more recently, on the experimental side, Nelson and Vitelli and others in 2007 did some experiments where they had a nematic shell with a double emulsion fluid, a drop inside and some fluid outside, and looked at the types of defects that you could get. And here they found that they could get 4 1/2 degree disclination lines, and this was the +1, 2 +1s in some other situations. And here they found in between they could get 1 +1 degree defect and 2 1/2 degree defects, depending on thickness and other parameters in the problem. And then more recently on Monday, Oleg Lavrentovich told us about experiments on lyotropic liquid crystals, in which in thin films he had a lot of +1/2 degree defects. And so my question, coming from the point of view of a PDE analyst, but also interested in the effects of materials and whether we can describe those through the models, the first question that I want to address is, do the Landau-Digen models exhibit the 1/2 degree disclination lines? Can we look at a minimizer and see that it would have to have 1/2 degree disclination lines, given some perhaps certain tangential boundary conditions and conditions on the sides? And this is joint work with Jinhae Park and with Dan Phillips, and I just want to give an overview, not go into a lot of the PD analysis, but give some idea of how it works. So here we consider a class of equilibria used to describe thin nematic liquid crystals with disclination line defects. And for this I used the Landau-Digen energy, but it's the elastic term without the L4 term, and then a bulk term with a large coefficient, epsilon to the -2, in front of it. And this is analytically to to give some emphasis or significance to the presence of that bulk term, and see that hopefully that would help to create disclination lines. And here I take a two-dimensional domain omega, so I'm thinking of an infinitely thin nematic liquid crystal and bounded smooth domain, and Q is a matrix valued function, as John Ball had described. It will have first derivatives, square integral, as well as the Q itself, be trace-free and symmetric. And we'll take some Dirichlet boundary conditions of non-zero degree on the boundary. And the tensor model here, I think we've seen a lot about this, based on a phenomenological theory. And here we imagine the Q to model the second moments of the average orientations of liquid crystals near the point X. And matrices in S have an orthonormal set of eigenvectors and have this representation. And for Q in S, trace-free and symmetric, I think we've seen this definition a few times. It's isotropic if its eigenvalues are all equal, uniaxial if exactly two are equal, and otherwise biaxial is one way to describe the phases. And here we are going to consider Q, not the general traceless symmetric, trace-free symmetric Q, but a Q in a subclass of that. I'll call it S0, where the 3,1 and 3,2 components are 0, and so by symmetry, so are these other two components. And the idea of this is that this is a way of ensuring that you always have tangential directions that are somewhat favorable, and E3 will be a principal axis of these eigenvectors, or will be an eigenvector, and therefore a principal axis of these matrices. And in that case, then, Q will have eigenvectors, two-dimensional, M1, M2, and 0, and its perk, minus M2, M1, 0, and E3. So it will have tangential directions, but it also has a vertical direction that's available to it. And of course, this includes matrices in this class with S1 not equal to 0 and S2 equal to 0. And now I'll look at the boundary value problem, as I mentioned. And we haven't assigned any boundary values. And also I want to say a little more about these terms. What are our assumptions on these? So here, the F sub E, the elastic term, is the standard one for the L1, L2, and L3 terms. And we're going to assume that L1 is positive and that the sum of L1, L2, and L3 is also positive. And the bulk energy density, we assume, is a smooth function of Q, non-negative, and that it's 0 if and only if Q is in this uniaxial, in basically corresponding to a uniaxial tensor associated to a vector M that's in the sphere. So we're assuming that's where the bulk term becomes 0, exactly where the bulk term becomes 0. And here S is going to be fixed throughout, this number S, and non-zero. And so the energy well is a set of uniaxial states. And we also assume that the F sub B satisfies the frame indifference that one would require for the bulk term. And we will have to add some additional structural assumptions to this F sub B in order to really get at the behavior. But whatever we add, which I'll mention later, I will require that it would include this standard example. So I want to be able to include this f sub b naught that we've been seeing. And here, if we take coefficients appropriately, we do have that f sub b naught is non-negative, and that this will become 0 if and only if Q is in this set of uniaxial states. And now boundary conditions. We take boundary conditions on Q, Dirichlet boundary conditions. Q naught is S times an N naught tensor N naught minus a third I. And we take that to be smooth, let's say C3. And the degree is defined through this N naught by this quantity. And this integrand basically just measures the angle, the continuous angle, d theta dt. If we took N naught and just started with a continuous description of the angle that it makes, then this would be d theta dt. And so going from its origin in its parameterization to the end, we would end up with something that could possibly be 1/2 degree, because we're dividing by 1 over 2 pi, and that would be a picture like this. And we're assuming that the degree of this is going to be some k. For Q naught, it would be called k over 2, and that k would be non-zero. So we have something of degree k over 2 if we're looking at the Q tensor, and of degree k if we're looking at n0 in the usual way. And then our problem is to investigate minimizers in A naught in the vanishing elastic energy limit as epsilon goes to 0 with these boundary values. And with those boundary values, you would expect to get you will get some defects. And this, actually, we came to this problem not through these more recent papers that I've mentioned on experiments, etc., but knowing that these disclination lines had not really been described for the general type of elasticity, and also through a paper of Schopel and Sluckin from 1987, where they looked at equilibria for this type of energy valued in S naught, which picks up these tangential but also vertical possibilities for the uniaxial solutions. And they pointed out that when you minimize in S naught, you still will have equilibria for the full problem. They will solve the equations that you need for the full problem. But at this point, I don't know if they are stable solutions. And so, and we also, through physics literature, found how to reformulate this problem in that space S0. In that space S0, we can make a change of variables for Q. And we can choose functions P1, P2, and R defined in omega. And we could represent Q instead of the Q11, Q12, which is Q21, and Q22, and then the Q33. We can just write these because they're trace-free as minus R, R over 2 minus P1, P1 plus R over 2, and P2's there. That's just a linear change of variables. And on the boundary of omega, since Q is Q naught, and Q naught is S times N naught tensor N naught minus a third I, we end up with having boundary values on the P1, P2, and R formed by just equating Q naught and this relation. And we find that if n naught is given by a continuously changing theta, then p naught is going to be s over 2 cosine 2 theta sine of 2 theta for its boundary conditions. And we see that r naught is going to be s over 3. And the degree of p naught, by the definition, will be k. And the length of p naught on the boundary is length of s over 2. And here, f sub b depends only on the invariance of q. And here, because q is trace-free, these are determinant of q, which is, in this case, length of p squared minus r squared over 4r, and also length of q squared, which in this case is 2 length of p squared plus 3 halves r squared. And what that means is that f sub b of q is, in fact, has to be a function of length of p squared and r, just from this invariance. And in this standard example, this is what it would look like in terms of length of p squared and r. And for q and s naught, remember that f sub b minimized at the uniaxial states associated with a vector m on the 2-sphere, but because it would be in S0, it would only be allowed to take either vectors m's that were in S1 cross 0 or E3 and minus E3. So that's something that happens when you restrict to S0. And if we change and look at what this means for G sub b of P and R, then it minimizes at this ring. Length of P is length of S over 2, R is S over 3, or the point 0, 0 minus 2S over 3. That's what corresponds to this director being vertical. And we have to have some conditions if we're going to try to analyze these solutions. And the structural conditions that we assume, which are assumed for the example we have in mind, are that in terms of length of p squared, which I call little p, and r, it's a smooth function, non-negative, 0 at this ring, and we saw it will also, for what we're thinking of, be 0 at another point. And the derivatives, g sub b with respect to r and length of p squared, should have some cubic growth, and that g sub b should be greater than or equal to a multiple of length of p to the fourth, length of r to the fourth minus 1. And that, for us, the benefit is that if you then get this integrable, then you get length of p fourth power integrable, and also r, fourth power integrable. And we also assume that g sub b near this well, that it grows quadratically away from that well, and that's for r close to s over 3 and length of p close to length of s over 2. And so we have something like this for our g sub b. And from the change of variables, then, we can reformulate the problem in terms of P1, P2, and R, and look at minimizing this energy, G sub E of grad P and grad R, plus 1 over epsilon squared times this bulk term that we've rewritten in terms of P1, P2, and R. And we're minimizing over A0, which just means over W12 functions, where P equals P naught on the boundary, and R equals S over 3 on the boundary. And here, the G sub E that I am using looks like this then. If L2 plus, here we assumed L1 was positive, but L1 plus L2 plus L3 was also non-negative, which means this sum could be non-negative or non-positive. So in this case, the G sub E looks like this. And if I look at, let's see, I want to look at this, and in the other case, L2 plus L3 is negative, then the G sub E looks like this. And either way, it's a quadratic, a very nice function, plus a non-negative quadratic. And in this case as well, this is a positive term. So it's non-negative, and it's got this nice term plus something non-negative. And that's very helpful. And main results, hope that this isn't too much notation. We can skip over the function spaces, but basically what we do is, here we have an epsilon, and we look at an epsilon as they go to 0. And what we have is that we can show that there's a sequence of minimizers for this functional. And for a subsequence, we can find a harmonic function. And basically, the length of pj's, so this is as epsilon j's go to 0, they converge to length of s over 2 outside k points. So there will be k points in the domain. And outside of those, length of pj prime is converging to length of s over 2. And the rj primes are going to s over 3. And for the pj itself, it converges to p star, a function p star, which looks like a product, e to the I times this sum of theta L. That's like a product of x minus AL over length of x minus AL, and then smoothed out by e to the IH. So we've got defects, A1 through AK. K matches the number of the degree of N naught, and those are where we're going to find disclination lines. And we have the structure of P, P1 and P2. Near there is like the product of x minus AL over length of x minus AL, smeared out by this rotation, e to the IH. And we also find that each Pj has degree 1 about those points. And that will mean that when we go back to Q, that each of those Qj's will have degree 1/2 about k defects that are in the problem. And we also are able to analyze the energy. And here, our G sub E, it differed by a null Lagrangian from the original F. If I just took F of Q of PR, G sub E differed by a null Lagrangian from that. And so our energy we can also analyze, and because of the null Lagrangian in the G sub E, it will differ by a constant. This is the constant. And the limiting energy of G epsilon minus this log is going to be, we can describe what that is. We can also describe where those A1s through AKs are. They basically organize themselves in the way that defects in superconductivity would. And I'll just mention that later. So here's the way that the A1 through AK arrange themselves. They want to minimize this reduced energy that is familiar in superconductivity. It's sort of like a, in some ways like a hexagonal or a certain way of packing. And this is because we took the epsilon to go to 0. And in that sense, it has some similarities with the Ginzburg-Landau functional in superconductivity, where you're just taking grad p squared over 2 plus 1 minus length of p squared squared. This functional is much more complicated, but that's the idea of why this might behave similarly. And then if I go back to the QJs, and see what do we have then. Well, what we've got is that the QJs, which correspond to epsilon being some epsilon j, they look like an Sj prime 1, that's a function of x, times this function, mj prime, tensored with mj prime, and plus another mj perk cross mj perk minus this. And the mj primes, through the change of variables, they look like cosine of the sum of just these azimuthal angles that you make, that x makes with each a sub l, and plus the hj prime, a C2 function. And the sj primes, the coefficients in front of these things, in front of the Q tensors that we get, they are formed by these linear combinations of Rj and length of Pj prime. So we can get a lot of detail out of this model by analyzing the problem in the PR variables. And the P, as far as the difference between Oseen and Frank and what we can do in the Q tensor is that because of the Q tensor, these things can be 0. And you have degree 1 defects, or P sub epsilons. They are degree 1 about these defects. And why can that be possible and still have, these are smooth solutions? It's because that the Pj, the P epsilons, are not length 1. So they're going to length of S over 2 most of the time, is what we're seeing. But they have defects, and those defects are allowed and don't violate the space that we're in because they are not restricted to be length 1. So they can dip down to 0 somewhere, and that allows them. That's why this is possible, and that's the advantage and what we were hoping for in being able to see defects with the Landau-Digen's type of functional that you cannot see in the Frank energy. And so this Qj prime, then, they converge to this uniaxial state, but that's away from the defects, and they can, and if S is positive and if S is negative, they converge to this one, and we have this formula for M, and it's a function of x in terms of azimuthal angles of x about the ALs and a certain harmonic function. And we have degree 1/2 about each A sub L. Difficulties in comparing to superconductivity, because we had worked in superconductivity before, in which this type of defect has been observed, degree 1, which here, through the theory, translates into a 1/2 degree defect. But here it's different. In Ginzburg-Landau, you have 1 minus length of u squared squared, so you have a connected well, and here it's a disconnected well. Also, here we have a coupled quadratic, the L1, L2, L3. Those are complicated terms. In Ginzburg-Landau, you're looking at grad u squared. And there's no maximum principle here. So those were things from the PD point of view that were difficult. And just to mention a few ideas, first of all, our choice of G sub E. It doesn't matter for the equations because they differ by the F sub E of the Q that corresponds to P and R by a null Lagrangian. But for other things like analyzing the energy near those defects, it does play a role. And here, what we do is for the F sub E of grad Q, which was originally given this way, you can subtract this, this null Lagrangian, and you get this term. And that is our G sub E of grad P and grad R when we make the change of variables. And similarly, in the other case where L2 plus L3 is negative. F sub E, we find if we add a null Lagrangian, looks like this. Grad Q squared plus curl of Q squared in that case. And the other thing that we do is this G sub E, it's a quadratic, it's positive definite. And for PD analysis, that's very good. And we do use the Euler-Lagrange equations quite a bit to get estimates. And for example, through the Euler-Lagrange equations and PD techniques, we can show this kind of an estimate, which we call a Poitzaiv inequality. And this is nice because remember G sub B was bounded below by length of P to the fourth plus length of R epsilon squared, or to the fourth, minus a constant. So this tells you that those are bounded. Those are bounded in L4, uniformly in epsilon. And we also get these kinds of estimates on the size of P epsilon and R epsilon. And right now, we don't really see that R epsilon is much smoother and much nicer than P1 epsilon, P2 epsilon, where you had a 1 over epsilon. We really have a defect that's leading to this log of epsilon measurement of the energy in that, near that defect. Here you can't see the difference, but later on we're able to show that, that actually our epsilon is bounded. Its gradient is bounded. That's not true for grad P epsilon squared, but we do get it bounded by a multiple of log 1 over epsilon. This kind of bound is very much like what we have in superconductivity. And in fact, if we combine this one, and we have this estimate, we prove that one, then the Ginzburg-Landau energy from superconductivity, if we combine these two, we actually get this, that Ginzburg-Landau superconductivity energy is bounded by this. And the theory says because P epsilon has length S over 2, this is the square of its length on the boundary, times pi k log 1 over epsilon. That by itself, plus the fact that, as I said, length of P naught is S over 2 and has degree k, that's what gives you k defects. As soon as we get that particular estimate, getting a different coefficient, this should be less than or equal to, getting a different coefficient than what is here, we wouldn't have these defects. We wouldn't be able to get them. And that is something that we learn from superconductivity. If we get a good enough estimate on the Ginzburg-Landau energy for all those P epsilons as epsilon goes to 0, then they have to have defects and they will have to spread out. They will have to have k defects. And so the lengths of let's see, go back. We have this as well. R epsilon, this estimate tells us that R epsilon is converging in L2 to S over 3, and that length of P epsilon squared is converging to S squared over 4. Of course, at the defects, that's not going to be true, right? We're going to have some zeros in order to compensate for the degree 1. So I think I will stop here, but I hope it gives you a flavor for what PD analysis and the Q-tensor Landau-Deschênes energy can give us, at least if we really single out the bulk term with the 1 over epsilon squared coefficient, which is analogous to taking very small elastic coefficient and looking at that.
Thank you. Time for a couple of quick questions before. Greg.
By the way, it's a very beautiful piece of work. What, it went over or past me or under me or something, but what were you able to say about the pores of the defects as a function of those elastic constants?
We were able, let's see if I can go back, just a measurement of the energy is what we
But were you able to characterize the degeneracy at the core? Do you know if it's
we
isotropic or
we don't know detailed properties of the core. And we would like to. For example, I think in your work, in Schopel and Slutkin's work, they did numerical computations, and they found that it would be strongly biaxial near the core. And that's a very interesting question.
Well, I'll show some numerical results about cores.
Yeah, so that's something that we would like to study. Here we've just found the core. We know the degree around it. We know the limiting energy and the way that the defects, how they form. But we don't know exactly what's going on in that core. That would be something for future work.
Antonio, you had a question.
My question is related to this. If one wanted to interpret your limiting theory after taking the limit as a director theory, so it's in plane and then there are some singularities, so can that be interpreted as escape, as a smart escape in the third dimension with a special structure of the core?
I think you can look at it in those ways. Yes, I do think so, yeah.
Yeah, at the back.
Well, your directors can't escape, can they? Because they're restricted to a plane.
Pardon? Well, no, but we have, for the P epsilon and R, which is the Q epsilon, you can go vertically.
But that's different. That's a kind of gone to a minus order.
Eigenvector, it's the eigenvector of the Q tensor that escapes in the third dimension.
Yes.
So discontinuously, just at that center point.
It's a degeneracy of the eigenvectors that's happening.
Right.
The principal axis is spreading to either a circle or the sphere, and that's what I was asking her, is do you know which of those is happening? Is it the degeneracy in the plane, or is one of the eigenvectors merging with the one that's orthogonal to the plane?
Point of degeneracy.
One of them is happening.
I'm pretty sure her hypothesis for the nature of Q insists that it stay in the plane and not go into the sphere. Because she has zeros on the...
Yeah, the zeros on the off-diagonal terms prevent what we would normally call an escape. I mean, what's conventionally...
But if the length of the in-plane director M goes to 0, it means that M is vertical, right?
If the length of the...
Modulus M goes to 0, it means that M is perpendicular to the plane, no?
Yeah, I guess so.
Can't completely go to zero because
So I guess, I mean, if you didn't have your restriction on Q to be for the director, as it were, to lie in the plane, then the true minimizer is actually when your elasticity goes to 0, the true minimizer are escaped defects. Because escaped plus 1 defects have S as the order parameter is constant. That would be the true minimizer if you allow Q to have non-zero elements in
Well, the thing is, the R is going to S over 3, and the P has degree 1, and that's what we know. And the P epsilons are all, everything's smooth, so it's in the limit we can imagine that. But for the actual solution, it is the Q epsilon where things happen, and I don't know what's
Perhaps we should continue this over coffee, which is being served now. Thank you very much.